Welcome to today's Explainer. We've got a seriously fascinating mystery lined up for you. We're looking at a recent guide from MarkTech Post, but we're going to treat the whole process of AI security analysis exactly like a high-stakes digital investigation. As AI skills get significantly more advanced and seamlessly woven into our daily workflows, making sure they're actually secure isn't just a best practice anymore, it is absolutely critical. So, grab your magnifying glass and let's dive right in. Imagine you're assessing a brand new AI skill. You run your standard security tools, and suddenly you get entirely conflicting reports. One tool says it's perfectly safe, while another flags it as highly suspicious. So who do you trust? How do we determine its actual safety? Well, this overarching mystery is the exact problem we're solving today. We're going to learn how to intelligently synthesize all these mixed signals to find the truth.
Here is our investigation roadmap. We'll outline the AI security challenge, load up our evidence, interrogate the scanners, visualize the clues, and finally, build the classifier. Let's kick things off with Section 1, the AI security challenge. This is really going to set the foundation for our entire cybersecurity investigation. To truly wrap our heads around this technical workflow, we need to view the ClawHub Security Signals dataset as our raw forensic evidence. The various security scanners, those are our witnesses, and just like human witnesses, they've got their own blind spots. Finally, our machine learning pipeline is the lead detective. It's the intelligence responsible for synthesizing all these conflicting clues to render a final accurate verdict. And this really gets to the core objective of the MarkTech Post tutorial. We simply cannot blindly trust a single tool. We have to dig deep and understand the underlying behavior of multiple security scanners before making any final judgment on a skill's safety. We really have to look at the whole picture here.
Moving on to Section 2, loading the evidence. Now that we have our mission, we need to securely acquire our data within our Python environment. Now, the setup here requires absolute precision. We first install our Python libraries and connect to the Hugging Face repository. Then, we combine the downloaded data shards into a single Pandas data frame. This gives us a really clean, robust split of training and test data to work with, ensuring our whole investigation is built on solid ground. Notice the specific engineering choice here, though, using Parquet files. By loading directly from the Hugging Face Parquet conversion, we completely bypass annoying metadata compatibility issues. It keeps our evidence incredibly fast to load, super clean, and entirely tamper-proof. It's a really smart move. All right, Section 3, interrogating the scanners. With the data secured, it's time to bring our witnesses into the interrogation room and see exactly where their stories disagree. So, we have 3 primary witnesses providing completely different types of forensic testimony. VirusTotal is looking for traditional malware using positive flags. Static analysis tools flag underlying code vulnerabilities using severity labels. And SkillSpector? That one provides numeric scores geared specifically toward identifying modern, AI-specific risks. Before we start analyzing their discrepancies, we need an objective polygraph test. The Jacquard score looks at the pure, raw overlap of positive signals. Cohen's kappa takes it a step further by factoring out random chance, essentially measuring true agreement. Together, these statistical tools tell us exactly how aligned or totally misaligned our witnesses actually are. And when we actually run the numbers, the results are pretty startling. These scanners often give entirely conflicting testimonies on the exact same AI skill. VirusTotal might look at a file and see absolutely nothing wrong, while SkillSpector is throwing up massive red flags. This lack of consensus is exactly why relying on a single tool is so incredibly dangerous today. If we just relied on one scanner, we'd literally be flying blind to entire categories of threats. We desperately need a unified approach to reach a safe final verdict. That brings us to Section 4, visualizing the clues. To make sense of all this conflicting testimony, our detective needs a murder board to spot the hidden patterns. First up, we have the overall class imbalance in the dataset across safe, suspicious, and malicious categories. Understanding this is absolutely vital. Think about it. If a dataset is 90% safe, a lazy detective model might just guess safe every single time and appear super accurate on paper. We have to know our baseline before we start training. Looking at the positive signal rates, we can clearly see the relationship between the raw scores and the final verdicts. This visual is great because it pinpoints exactly which witness tends to consistently overreact and which one constantly misses the subtle clues. Finally, Section 5, Building the Classifier. It is time to construct our ultimate solution, the machine learning lead detective. Here's the high-level architecture. First, we extract TF-IDF text features from the SkillMD file, essentially turning the suspect's written code into a mathematical fingerprint. Then we gather our hard numeric scanner signals, stitch the whole thing together, and train a logistic regression model to review the evidence. Notice the explicit mix of features fed into this pipeline. We aren't just relying on numbers, and we aren't just relying on text. We're feeding our detective the deep text-based context alongside the VirusTotal flags, the severity labels, and those AI-specific SkillSpector scores. By uniting both textual and numerical clues, this straightforward logistic regression model becomes highly effective. It learns exactly how much weight to give each witness depending on the context of the file, predicting the final verdict with impressive accuracy. It's simple, but it's incredibly robust. But hey, a good detective always reviews their closed cases, right? We evaluate performance using a classification report and a confusion matrix, which is a tool that shows exactly where the model gets confused between categories. We also review sample misclassifications to understand exactly what types of files still manage to fool the system. To wrap up this explainer, we have successfully journeyed through a complete analytical workflow. We've seen how to logically step through exploratory data analysis, gracefully handle conflicting security signals, perform feature engineering, and ultimately solve a complex AI challenge using a unified machine learning pipeline. I'll leave you with this final thought to spark your curiosity. As AI models scale into fully autonomous agents acting on our behalf, the skills they use will become exponentially more complex. If our basic security scanners regularly disagree this much today, how will we secure the AI agents of tomorrow? Building intelligent, synthesizing classifiers isn't just a fun coding exercise. It is absolutely essential for our future safety. The investigation is really just beginning. Thanks for joining me for this explainer, and I'll catch you next time.